This is the Graphing Equations tutorial. In this tutorial, we will learn how to find intercepts algebraically from an equation, how to test an equation for symmetry with respect to the x-axis, the y-axis, and the origin, and also we will learn how to graph key equations. The first important concept covered in this tutorial is finding intercepts graphically from equations. There's a two-step procedure for finding intercepts. First, to find the x-intercepts, if any, of the graph of an equation, we need to assume y equals 0 and solve for x. Next, in order to find the y-intercepts, if any, of the graph of an equation, we will assume x equals 0 in the equation, and then we will solve it for y. Let's see how this rule applies to a real equation. Let's assume the equation we have is x squared minus 4. Okay, so in order to find the x-intercepts, first we will solve for x with y equal to 0. So the first step that we will do is we'll set x squared minus 4 equal to 0. We'll go ahead and factor x plus 2 times x minus 2, we'll set that equal to 0. Factoring out, we get x plus 2 equals 0 or x minus 2 equals 0. And using zero product property, we come up with x equals negative 2 or x equals 2 when we solve the equation. Next, let's go ahead and find the y-intercepts, assuming x equals 0, and solve it for y. So to solve for y, we'll set the equation y equals x squared minus 4, and then we'll go ahead and set that, having x equal to 0, so we have 0 squared minus 4, which would equal negative 4. So the equation has two solutions for x equals negative 2 and 2, and then we find out that when we solve the equation we get y as negative 4, the y-intercept therefore negative 4. Now we can plot the points on the graph by hand and see what this equation looks like on the graph with the intercepts. When we plot the points on the graph on the right, we can see that we get 0, negative 4, negative 2, 0. Continuing on along, we have negative 3, 5, and 3, 5. So when we connect the dots to this equation, we will see that it looks something like this. So that is the graphic picture of the equation x squared minus 4. Let's try one more example that asks us to find the intercepts of the following equation. In this example, we are asked to find the intercepts of y equals x squared minus 4 divided by x squared plus 1. We know from the previous example that we first need to determine the x-intercept by letting y equals 0, solving the equation for x. And secondly, we need to determine the y-intercept by letting x equals 0 and solving the equation for y. First, let's go ahead and solve the equation for x. Our first step is to go ahead and set the equation equal to 0. So we have x squared minus 4 divided by x squared plus 1 equals 0. Our next step is to multiply both sides by x squared plus 1. When we multiply both sides by x squared plus 1, the result that we get is x squared minus 4 equals 0. We factor and we get x equals negative 2 or x equals 2. So we know the x-intercepts are negative 2 and 2. Next, we need to obtain the y-intercept by letting x equals 0 in the equation and solving it for y. So we will plug in 0 for the x. In this example, we'll have 0 squared minus 4 divided by 0 squared plus 1. And we'll go ahead and factor that out. We get negative 4 divided by 1, and continuing with the math, we get y equals negative 4. So the x-intercepts in this equation are negative 2 and 2, and the y-intercept is negative 4. So therefore we know our intercepts are negative 2, 0, 2, 0, and 0, negative 4. We can go ahead and plot those points on the graph to the left. 0, negative 4, -2, 0, and 2, 0. So when we go ahead and plot the points on the graph, we end up with a graph of the equation looking something like the graph on the left for y equals x squared minus 4 divided by x squared plus 1. The next important concept in this tutorial is determining symmetry in equations. Graphs of equations can have symmetry with respect to one of the coordinate axes or with respect to the origin. Symmetry with respect to the x-axis simply means that if the Cartesian plane were folded along the x-axis would coincide with the portion below the x-axis. Symmetry with respect to the y-axis or the origin can be described in a similar manner. There are three graphical tests for symmetry. First, regarding the x-axis, if for every point xy on the graph, the point x negative y is also on the graph, then we know the graph is symmetric with respect to the x-axis. Next, if for every point xy on the graph, the point negative xy is also on the graph, then the graph is symmetric with respect to the y-axis. And lastly, if for every point xy on the graph, the point negative x, negative y is also on the graph, then the graph is said to be symmetric with respect to the origin. Let's see how this works as we take a look at the three different graphs. We can see from the three different graphs below the different types of symmetry. First, symmetry with respect to the x-axis. You can see on this graph that the portion above the x-axis, the xy coordinates, are reflected as if we were to fold the graph along this x-axis here. It's exactly a mirror image of x with negative y. Next, symmetry with respect to the y-axis. We see that if we were to fold the graph here along the y-axis in half, we would get exactly the same mirror image of negative xy as xy. So we have points on this graph such as negative 6, 3, and also 6, 3. And you can see we have 9, 6, and negative 9, 6. Lastly, symmetry with respect to the origin. In this particular example, we have symmetry here with xy, this point, 4, 4, and also on this graph, negative 4, negative 4. So we have negative x, negative y, and xy. Those are the three types of symmetry in graph form. In addition to graphing, we can also test for symmetry using algebra. With regard to the x-axis, if replacing y with negative y yields an equivalent equation, then the graph is symmetric with respect to the y-axis. With regard to the y-axis, if replacing x with negative x yields an equivalent equation, then the graph is symmetric with respect to the y-axis. And lastly, regarding the origin, if replacing x with negative x and y with negative y yields an equivalent equation, then the graph is symmetric with respect to the origin. Let's go ahead and see how we can test for symmetry using algebra in the next example. In this question, we are asked to draw the graph of the following equation using symmetry, and the equation is x minus y squared equals 1. So let's go ahead and solve that algebraically and see what the graph looks like. Of the three tests for symmetry, the only one that is satisfied in this equation is the test for x-axis symmetry, because x minus negative y squared equals 1 is equivalent to x minus y squared equals 1. So the graph is symmetric with respect to the x-axis. Using symmetry, you only have to find the solution points above the x-axis and then reflect them to obtain the graph, as we will see on the graph on the left. We can go ahead and place our solutions in a table which looks something like this here on the right. We have y equals 0, we solve the equation, we get x equals to 1, so we have points 1, 0, 0.21, and 0.52. When we go ahead and graph those points, you will see the equation looks something like this. We can go ahead and plot the points from the equation, getting 1, 0, 2, 1, 2, negative 1, 5, 2, and 5, negative 2. Then we'll go ahead and connect the lines between the points, and that is the graph of the equation x equals y squared plus 1.